In this video, we will discuss the notes for 1.3, diffusion. Recall that our fundamental conservation law is listed here. The partial derivative of u with respect to t plus the partial derivative of phi with respect to x equals f, where u is the density of a physical quantity, phi is the flux, and f is a source. All of this is happening at some point x and at some time t. When there is no source, in other words, when f is equal to 0, the conservation law becomes what you see here. The partial derivative of u with respect to t plus the partial derivative of phi with respect to x equals 0. Or in other words, u sub t equals the opposite of phi sub x. This represents how changes in density relate to changes in the flux, at least locally. When phi is proportional to u, we get advection. In this section, we model a simple diffusion process where movement is based on random collisions. We start with two observations. The first observation is that the movement is from higher concentrations to lower concentrations. And our second observation, the steeper the concentration gradient, i.e. the derivative, the greater the flux. Condition 2 implies that the flux should, in some sense, depend on the partial derivative of u with respect to x. We will assume that there's a linear relationship. This is known as Fick's law. So we will assume that the flux phi is equal to minus d times the partial derivative of u with respect to x, where d is some positive number called the diffusion constant. We assume that d is greater than 0, so that if the partial derivative of u with respect to x is negative, then phi will be positive and the flow will be to the right. We call this down the gradient. If the partial derivative of u with respect to x is negative, that means that u is decreasing as we move to the right. And since the flux is moving down the gradient, it will be moving to the right, which is the positive direction. Note that d has units length squared per time. So what do we have so far? We have our conservation law, u sub t plus phi sub x equals 0. And we also have Fick's law, which tells us the relationship between the flux and the partial derivative of u with respect to x. So if we combine these, we get what we call the diffusion equation. So if phi is equal to minus du sub x, then phi sub x is the derivative of that. So it's minus du sub xx. So if we take that and plug it into our conservation law, then we have that u sub t is equal to minus du sub xx, which is what we have right here. That just goes right there. And this is equal to 0. So this is just our conservation law combined with Fick's law. That gives us our diffusion equation. In the next line, we just simply add the d times u sub xx to the other side, and so that we have the partial derivative of u with respect to t is equal to some constant times the partial derivative of u with respect to x twice. So if the concentration profile is concave up, what does that mean? If the concentration profile is concave up, that means that the second derivative with respect to x is positive. So that means that you have an image that looks like this. The image is concave up. The second derivative is positive. Now, if the second derivative is positive, d is also positive, so that implies that u sub t is positive. So if the graph is concave up, then u sub t is positive. That means that u is increasing as time goes by. So that means the concentration is increasing as time goes by. So if you have a graph that's concave up, then u is actually moving up as time passes. Similarly, if we have concave down, where the second derivative of u with respect to x is less than 0, that means u sub xx is negative, so u sub t is also negative. If u sub t is negative, that means that u is decreasing. So if you have a graph that is concave up, you'll have that the graph itself is moving upwards. And if the graph is concave down, then the graph itself is moving down. So there is a leveling effect or a flattening effect at work here. Let's talk about heat conduction. We consider heat flow in a one-dimensional bar having a constant density ρ and a constant specific heat C. The specific heat, or the specific heat capacity, which is why it's called C, is the amount of energy required to raise a unit mass of material by 1 degree. It's given in units of energy per mass per degree. We will apply our conservation law to the bar. Our conservation law is the partial derivative u with respect to t plus the partial derivative of phi with respect to x is equal to 0, where, remember, u is giving us a density of some kind, and phi is a flux. Now, in this particular case, u is going to be defined to be ρ times c times theta. Now, u is the energy density, and theta is the temperature at a specified place, x, and a specified time, t. So u is our energy density. The conservation law in this case becomes ρ times c times the partial derivative of t with respect to t, the partial derivative of theta with respect to t, plus the derivative of flux with respect to x equals 0. This is our conservation law in this case. This is telling us that we have energy balance in the bar when no sources are present. Now we make an assumption about the flux. This is known as Fourier's heat law. And what does it tell us? It tells us that the flux phi is equal to negative k times theta sub x, where k is some constant called the thermal conductivity. This is a capital K. So Fourier's heat law tells us that the flux is proportional to the derivative of the temperature with respect to x, where our constant of proportionality is negative k. That negative is here for the same reason that we had a negative before. Heat flows from hotter regions to colder regions. That is, it flows down the temperature gradient. If your partial derivative with respect to x is greater than 0, that means the temperature is increasing. And in other words, the flux is negative. The flux being negative means that it's moving to the left. So as you can see here, in this sort of very rough drawing, if theta sub x is greater than 0, that means that it's increasing as x moves to the right. So you have a slope that's upwards like this. We want the flux to be moving down the gradient because we're going from higher temperatures to lower temperatures. So higher to the right means that the flux is moving to the left because, of course, heat flows from hotter regions to colder regions. So the conservation law now becomes, with this additional information from Fourier's heat law, the conservation law now becomes what we have here. So we have ρ times c. Remember, ρ is the constant density, c is the specific heat, and theta is our temperature. So it's the rate of change of the temperature at a time t, plus the derivative of flux at a time at x. The derivative of flux with respect to x, that is. So ρ times c times the partial derivative of theta with respect to t, plus the partial derivative of phi with respect to x is equal to 0. That's our conservation law. And here we have Fourier's heat law. But of course, what we're interested in is the partial derivative of flux with respect to x. So if phi is equal to minus k theta sub x, then the partial derivative of phi with respect to x is minus k times theta xx. So there we have the second partial derivative of theta with respect to x. So we just take this value and plug it in right there. Well, not where the sub x is, right there. There we go. And what do we end up with? We end up with rho times c times theta sub t, and now our plus phi sub x becomes minus k times theta sub xx. So again, if we highlight it, phi x is equal to all of this. Phi sub x. So this is what our conservation law looks like. The next thing we do is we divide by rho times c. So we're dividing by this term, so you can see it here. And of course, 0 divided by rho times c is going to still be 0. This k is a capital K. We're now going to introduce a lowercase k. So we're going to let lowercase k be equal to the coefficient there in front of the theta sub xx. So lowercase k is equal to capital K divided by rho times c. This is known as the diffusivity. And what we end up with is precisely the heat equation. So we see that we have the heat equation as a consequence of our conservation law, together with our assumption that came from Fourier's heat law.